doing in Google Brain for almost 4 years now, and I've been working in collaboration with the machine learning compilers at Google. In this talk, there will be the combination of both focus on the machine learning compiler techniques and also the application of machine learning for compilers. As the title say, machine learning for machine learning compilers. And so the goal of the project that I've been working on is to basically figure out if there's a way to automatically set the best compiler configuration for all the machine learning workloads that run at Google. So before we dive into what exactly I'm doing, first we need to understand what machine learning compilation stack at Google looks like. So you might be familiar with the top layer, which is basically the user-facing framework for programming machine learning workloads, right? So you know that Google invent TensorFlow, now JAX is coming, and a lot of researchers also use JAX at Google. And outside Google, a lot of researchers use PyTorch. So you might be familiar with these frameworks. At Google, there is the compiler, which is basically the backend behind these high-level framework. And the job of the compiler is to basically translate from the tensor computation graph that the user specify in the high-level language, whether it's TensorFlow or PyTorch, and then translate that into the back-end hardware, whether it's calling library or generated code for different hardware. And the main hardware that we use at Google is CPU, GPU, and TPU, which stand for Tensor Processing Units. The majority of machine learning workloads, especially for training workload, it's running on TPU now at Google. So the work that I'll be talking today will focus on the TPU backend. But the techniques or the methodology can also apply for other backend as well. All right, so I talked about compiler, so let me define what exactly is the compiler for those of you who might not be familiar. So compiler is basically a tool that transforms program written in high level. Basically, when you write program, right, like those are written in high level language, it translates that into low level representation, whether it's machine code or some sort of intermediate representation. And as part of transforming the program, it also optimized the program for performance, usually optimizing to have faster runtime through different various optimization, which is done using heuristic. So usually these optimization is quite complex. It's usually combinatoric. And if you want to find the optimal solution, usually you have to do exponential algorithm. But you can't afford, a compiler can't afford to take that long. So usually the compiler developer usually derive a pretty fast algorithm, usually in polynomial or linear time, to basically solve this problem. So now there's a trade-off, because when you solve these combinatoric problem really fast, you might get suboptimal solution. Now, what I do is I build autotuner for compiler, especially specifically for the XLA compiler. The autotuner is essentially it assisting the compiler to find better optimization decisions, right? As I talked about, those heuristics could be suboptimal. So what autotuner does is that instead of using heuristic, it will search the space of all possible configuration for that particular program being compiled. And then it will try to select the best configuration according to some performance metrics. And for example, it could be optimizing for the fastest runtime, or it could be the smallest memory consumption, for example. So we have built the autotuner for XLA TPU compiler specifically. And this slide summarizes different various optimizations that happen in the XLA compiler. Now, XLA compiler is different from traditional compiler, for example, C++, because it is a compiler for domain-specific language, right? Like, we know that people use this to program machine learning workloads. So there's a lot of optimization that you can do when you have the domain-specific knowledge. So there are I would say, two classes of optimizations that happen in XLA. The first one is graph-level optimizations. These are optimizations that you need to do when you have the knowledge of the entire graph or the program. So graph here essentially represent machine learning workloads. Each node is high-level operation like convolution, metric multiplication, or ReLU, for example. And the flow is basically the data or the tensor that flow from one operator to others. So the program can be represented as computation graph. And graph level optimization, there are a lot of them. For example, one that it's common, it's layout assignment, which is the optimization that think about how would you lay out the high dimensional tensor in the physical memory, like which dimension should be the major dimension, which one should be in the minor dimension, right? And you have to do this for all the intermediate tensor in the program. Another example is operator fusion, where you can fuse these nodes, some of the nodes together. By fusing means that you essentially like reduce some of the memory traffic, which I'll go into detail a bit later. Now, once you have once you make the graph level optimizations decision, you end up with something that we call kernel, where each kernel is basically these, for example, the box, these, squarish box that I draw here. Kernel usually contain a few of the ops or the nodes fused together, meaning that we already decide that, okay, these ops should be fused together to form a kernel. And in a lot of the backends, we tend to run one kernel at a time. So, which means that different kernel don't run in parallel, they don't run in concurrent, so they don't interfere each other. So, which make optimization decision somewhat easier, because now what you can do is that you can find the best configuration for the kernel without worrying about other kernels running at the same time. So we call these kernel level optimization. These things includes like what is a loop tiling structure of that kernel, what would be the tiling size, for example. All right, and in this slide, I also highlight some of the optimizations in colors. These are the ones that we already have support for auto-tuning, where orange one is the one that, that we have supported and deployed to use in production. The blue one is ready to be deployed, and the green one is under active development. So now let's me explaining how exactly what are the different components of the autotuner and how we build the autotuner. So in here, obviously there are optimization problems that we would like to tune. When we tune a configuration for these optimization, we need to evaluate for its performance, right? Like whatever it's a runtime or energy consumption or whatnot. So the way we evaluate for a candidate is to compile and then run them on the real hardware. So that's the bottom part of the figure. And here's where machine learning comes in. Right? Sometimes it takes a while to actually evaluate each candidate. It takes some time to compile and run the program on the real hardware. So instead of evaluating a candidate on the real hardware, what we could try to do is to use a machine learning model to predict the runtime or whatever the performance metric we're interested in, instead of having to compile and run on the real hardware. Another place that machine learning can come in is also guiding the search directly. So perhaps we can say, let's try this configuration next to make it faster to converge to a good solution. So that's the overview, and let me dive into each of the components. The first one, let's understand how we define the search space for these different optimizations, right? Which actually really important because it dictates like how fast you can actually converge to find a good solution. So we first define a path configuration for the optimization path that we're interested in. And the configuration is specific to the tensor computation graph. In particular, a configuration for a graph is actually a collection of per node configurations, which then control how the compiler or the path transform the graph. Let's take a look at a concrete example for layout assignment paths. So as I said earlier, the layout assignment paths essentially have a responsibility to assign physical layout for each of the tensor in the graph, right? So here we specify a configuration for each node in the graph. So for this node, for each node, we essentially specify the configuration that will dictate what is the physical layout of its input and output, right? And as you can see here, that tensor, or the edge that flow from one node to other, that's represent a tensor. Sometimes the configuration that's specified can be conflicting. In this particular case, on the edge that I highlight the red color, you can see that the output of add have a different physical layout from the input to convolution. So what happened here is that the compiler would then have to fix the physical layout to be matching by inserting the layout correcting operator, which we call a copy, because it doesn't really do much. It just changed the layout of the tensor. And the goal here is that we want to find the configuration such that for each of the compute node, they run fast, but also not incurring too much copy operation, right? So to define a search space, naively what you could do is that you can specify layout for each of the input and output tensor independently by considering all the permutations of their dimension. However, there are a lot of constraints between tensors within an operation or between the operation. So considering defining search spaces this way will actually result in a lot of invalid configuration because it's ignore all the constraints between these tensors. So instead of doing that, what we do is that we consider tuning the layout options for important ops that will affect the layout quite significantly, and these include things like convolution operations and reshapes. And once we make decision for important operation, so I said that there are constraints between tensors, right? So how do we get that constraint? What we can do is that we can consult the compiler, which basically have the knowledge about the constraints of these ops. So we can consult the compiler to get the list of all valid input-output layout configuration that we can consider. Once we choose a valid configuration for each of the important ops, like convolution and reshape, we also use a layout propagation in the compiler to propagate these layout to other nodes in the graph. So when you compare these search space, compared to the naive version, it is a much, much more compact search space, and it only include valid configuration. So we ran a quick experiment that compared the effectiveness of these different search space. And as you expect that the proposed search space is much better than the naive version. So these are the speedup found by the autotuner using different search space, right? So higher is better. Right, let's take a look at another example. Here is an operator fusion optimization. In here, the configuration that we annotate at each node dictate whether we should fuse that node or not to its consumer, where one means we want to fuse that node to all of its consumer. So the resulting graph, as you can see here, that add get fused with reshape and copy, right? And what does it mean by fusing these operators together? When you fuse operators together, it means that the intermediate output from the first operator can be used right away by the consumer. It does not need to be saved in the main memory, which means that we can reduce the memory usage and also the traffic to the memory, right? So it's good for that sense. However, there's a trade-off, as you can see here, that when add have two consumers, when we fuse adds to copy and reshape, we need to recompute add, right? So fusion can incur recompilation. So this optimization is not obvious because you have to trade one for another things. So the way that we define the search space for Fusion, it's quite simple. As you can see here, we can basically consider whether each node is 1 or 0, right? So that is one of the search space that we can try. Well, but there are alternatives. The other one is, instead of considering a configuration per node, you can consider a configuration per edge, which is more fine-grained, more expressive, but that also means that the search space will be larger because there are more number of edges than nodes in the graph. The other thing we try is also a per node configuration, but instead of controlling the Fusion behavior directly, we control the priority value, which is something that the internal the internal heuristic in the compiler used to make the decision. Right, so it's basically, oh, this one is easy to make it work with the current compiler, so we try that. The other one that is very different from the other three is, instead of controlling the node or the edges, what if we define some parameters that control the heuristics in the compiler? The advantage of this one is that there are only a few flags that we need to specify, and it does not depend on the number of the nodes or edges in the graph. So the search space can be extremely small, and it doesn't grow according to the size of the graph, right? So these are the 4 things that we try, and here is the result. Again, higher is better. From the result, you can see that the per node and per edge are doing equally well, where per node is slightly better, where the other search space, like node priority and flags, are doing much worse. So in our current autotuner, we go with the per node configuration. Yep, question?
That seems counterintuitive, right? Because per edge seems more expressive than per node. So why is this not?
I should repeat the question, right? Yeah, so the question is that since per edge configuration is actually more expressive than per node, why is per node is the best here, right? Which is somewhat counterintuitive. I think that it's true, given, I think like if you actually have, if you have longer time that to explore exhaustively, then the per edge should be the best for sure. But since the search space is so large, you can cover all the search space. The per edge end up having a much larger search space than per node. So in that sense, per node is more effective. Yeah. Yeah, so I think basically the lesson that we have here is that, before trying any like fancy search algorithm, so I'll go into later of like the search algorithm we do. The results here is all simulated annealing, which is very basic. The lesson that we learn is that, despite looking at more fancy search algorithm, what is very important is how you define the search space. All right, and next, this is the last example that I have, and these are the optimization at the kernel level. So the optimization that we support auto-tuning is to select the best or tile size for each of the kernel, and also some low-level parameters for the code generation. And as I say, since we can tune each of the kernel independently, this problem becomes somewhat easier than the graph level. And for each of the kernel, we can also enumerate all possible choices, unlike at the graph level where the search space is exponential in terms of number of nodes and edges. For the kernel level search space, most of the time we can enumerate them all and do exhaustive search. All right, so let's put everything together. So we run our autotuner, including layout tuning, fusion, operator fusion tuning, tile size selection, and some of the low-level code generation tuning flags. We tune about 150 machine learning workloads collected from both production and research models at Google. And this chart shows the workloads that achieve 5% or more improvement. And you can see that some of the workload, like the first one, AV speech, we gain up to 2.4 times speed up over the baseline, which is the default production compiler. And a good number of benchmark, about 13% of the benchmark in this benchmark suite, gain more than 10% speed up. However, there's a caveat because, as I say, autotuner performs search over the search space, so it takes time, right? So in this experiment, we allocate about 1 hour to tune each of the optimization passes. So naturally, the next question is how to make this faster, right? And the first technique that we are looking at is to use machine learning to try to predict the runtime for these programs. As I said earlier, the graph can be composed into individual kernels, right? So what we can try to do is to use machine learning to then predict the runtime for each of this kernel. Once we have the runtime of each of the kernel, it is not too difficult to then estimate or infer the runtime of the whole graph. And since the kernel can be naturally represented as graph, there are usually smallish graph about 10 nodes or less. We consider using graph neural network to model this problem. And for the input to the model, we consider using opcodes ID, which represent the types of operation for the node. For example, matmul, convolution, and so on, right? And we use a learn embedding table to do a table lookup to convert the opcode ID into opcode embedding. And in addition to just the types of the node, we also consider other important information such as the size of the input and output tensor and auxiliary information such as striding or padding size. So those are in the extra node features here. And then we also talked about configuration for the graph, whether it is a per node or it is a feature configuration like tile size. These can be represented by repeating the feature and concatenate them with the node features. And so these are input that we then feed to the GNN model. The output of GNN is node embeddings that then can be reduced into kernel embedding and feed that into a feed-forward layer to predict the final runtime. The reduction model, we consider multiple options, including just simple reduction where you basically just reduce the embedding all over all the rows into one row, or something more fancy like LSTM or transformer. Now let me zoom into the GNN model a little bit, and maybe some of you might be familiar with this or not. I'll just recap it a little bit. So the way that graph neural network works is that to compute the embedding for a node in the graph, you consider aggregating the embedding of the nodes that nearby, right? So in here, if you try to compute the embedding for this node in red, and let's say that the GNN have depth 2, you end up considering the nodes that are in 2 hops away. GraphSage is a type of GNN that basically, instead of considering all the nodes, all the neighbors, for example, here for red, you might end up ignoring some of the neighbors, and these end up actually showing a better generalization. So we use GraphSage in particular for our cost model. And here is some formulation if you want to see some math. So here is the embedding for node I, and the K is representing the depth of the GNN. So when we compute the embedding for node I at depth K, we essentially concatenate the embedding at the different depth of that node, concatenate with the embedding of its neighbor, passing through a feed-forward layer. And once we concat everything together, we pass that into another feed-forward layer and L2 norm layer. All right, so now that we have the model, the other thing that we need to consider is what is the loss function that we use for training. We consider 2 types of loss. One is just mean square error, right? So this is, you can think of this task is basically a regression task where the target is basically the real runtime, and we want the model prediction to match the target. So naturally, the most common loss people use is mean square error, so we consider that. But we also consider pair-wide rank loss, and this is because in some tasks, we don't we don't really need to predict the absolute runtime. We only care about the ranking between the configuration, right? Given the kernel, we just need to know what is the best tile size, for example. So we don't really need to predict the absolute runtime. We just need to select the best one. So we consider using pairwise rank loss as shown in the second equation. And the two types of tasks that we are considering when we develop the cost model is the tile size selection. So for this one, as I said, we mostly care about the relative runtimes or the ranking. We also evaluate this on fusion, essentially given a random fusion operation or like arbitrary fusion operation or kernel. Let's try to predict the absolute runtime. And this is useful because when we have the entire graph, you can predict the runtime for each of the kernel fusion. And then you can then sum or like weighted sum these up to predict the whole runtime of the graph. And the baseline that we compare our cost model with is a handwritten model that is used in the compiler. It's built specifically for tile size selection. And we also adapt this cost model to use for the fusion task as well, but it's not built specifically for fusion tasks. So our data set is essentially drawn from the auto-tuning data set where we have about 100 XLA graph of programs. And then we essentially run the tile size auto-tuning to basically generate for each kernel, try different tile size, and then you get different runtime, right? So we enumerate for each kernel, we enumerate all possible tile size to generate the runtime. For fusion workloads, we instead of using the default fusion configuration, we randomly generate different random fusion configuration to get different arbitrary fuse kernel. And then each of them, we then use the default tile size to get the runtime. So overall, there are about like 100 graphs that we use to generate the data, but the data point itself is quite high because for each of the graph, there are a lot of tile size and fusion configurations. So we have about like 10 to 100 million data points. All right, and here's the result. So this is for tile size selection task. So for this, we essentially report the error, the lower is better, meaning that for each kernel, we have all possible tile size, and then we use the learn model or the cost model to basically select which one is the best tile size, right? And then we compute the difference of the best according to the model with the ground truth and see the difference, right? So if the model is accurate, the error would be 0. And the first column is the error from the learn cost model, and the second one is the error from the baseline analytical cost model developed by the compiler developer. And you can see that for all of the benchmarks here, the learn cost model beats the baseline, where there's only one problem that the baseline is doing better. And the error itself, it's quite low. You can see that's only a few % error. And on the second task, which is more difficult, the learn cost model is still doing pretty well, and indeed a lot better than the baseline. And this is because the baseline is not developed specifically for this task, which also highlight the advantage of doing a learn cost model, because when you already have the learn cost model, you just need to feed it the different data and then you just let it run and then you get the learn cost model. Where to build an analytical cost model, sure, you can adapt one cost model for another, but you can see here that the performance is not that good and it takes a lot of time to really improve the analytical cost model. All right, now some key takeaway that we got from experimenting with the learn cost model. We learned that for a task that you only care about the ranking and not the absolute runtime, using rank loss is actually much better. So on like the tile size prediction task, right, we can see that using the rank loss, it's much better than using MSE, and it actually improved the error by almost like 10 points. And we try a bunch of different reduction model. So for GNN itself, we try GraphSage, we try graph attention networks, and which the graph attention network or gate is actually more expressive than GraphSage. However, in our experience, it's much easier to train GraphSage, and GraphSage model end up having a better accuracy. And for the reduction model, we also consider other sequence model like LSTM and transformer, instead of using a simple non-learned reduction model. And we found that it helps, but just only a little bit. So if we are interested in, like having a smaller model, better runtime in terms of inference, then using a non-learned reduction seems to work pretty well already. All right, so now that we have the learn cost model and verify that their accuracy is pretty good, we then integrate this into the autotuner. So we trained a model for the tile size selection, for the low-level code generation, and also graph-level optimization like layout and fusion. And we integrate this to the autotuner by essentially just replace the evaluation with the learn model. And then we collect the top K configuration according to the learn cost model, and then only execute those top configuration using the real hardware. And here's the result. Right? So the left bar is when we learn the cost model, and on the right bar is when we use the real hardware. So, and we are, in this experiment, we give a lot of, a large timeout. So the one that use hardware is basically the optimal that you could reach. So we try to demonstrate that when you use the learn cost model and only execute the top K on the real hardware, you can find the configuration that's almost as good as the optimal. Where if you look at the tuning time, you can see that using the learn cost model can reduce the tuning time significantly. Especially this light blue bar represent the time that only need to run on CPU. So if you only look at the time that needs to run on the real accelerator or TPU, you basically exclude the light blue time. It is actually really small compared to the time required by when you need to use the real hardware every time. And so we deployed this learn cost model in the production compiler. And one trick that we learned is that we have to make sure that our model is up to date to the current workloads that we see. So in machine learning, we know that out of distribution is a real problem, right? Where you train model on your training set, and then you deploy the model. Sometimes the data that the model see in real time, it's actually much different than the training data set. So the accuracy might get degraded over time. So the way that we deal with this is that we fine tune our model every day. Not the whole model, because that it takes time to update all the weights in the model. So what we do is that we freeze the GNN parts of the model and only fine tuning the prediction head, the last feed forward layer. So we tune with the real data every day. We also have an additional input to the final layer head for different types of accelerator. So it turns out that Google essentially develop new TPU generation quite often, like almost every year. So instead of having different model for each of the TPU generation, we share the GNN parts and only train different heads for different types of the generation. And also you can see that we also can use the GNN model for different types of optimization as well. So we end up using the same GNN for both tile size and the flag selection tests. And we deployed this in production, and we found that this technique actually helped speeding up the tuning times by almost 20 times. All right, so far I mainly focus on the learn cost model before I moves on, maybe anyone have questions?
it affects like which kind of graph algorithm?
Yeah, so the question is that what are the sizes of this graph? Because the size of the graph also affect what kind of learning algorithm we might want to use or the model we want to use. So for the kernel level learn cost model, which I have been talking about, those graphs are fairly small. So I would say on average, they're about 10 nodes in the graph. So I think that the GNN is still quite effective because we are using about like 3 or 4 layers of GNN. So it cover like almost of the graph already, right? But which is a great question as a transition to this one where we also try to now use the learn cost model to predict the whole graph runtime, right? Instead of at the kernel. Now, the graph, the whole program graph is actually huge, like really large. On average there, I think it's about 10,000 nodes in the graph, but I have seen as large as like 100,000 nodes in the graph. So we try to scale this to work at the graph level, and it doesn't work quite so well. And the first obvious problem is the fact that the graph is really, really large, right? We also tried this with like LSTM and transformer, but obviously those one doesn't scale either. I think in like NLP domain, usually the sequence length is not that large, right? It's about 1,000-ish, not like 100,000. And the other problem is also that it's really hard to fit these large graph in the device memory for training. And so like, how do we deal with these large graphs? So that's an obvious question. And this is something that we still actively working on. We have not published this part yet. So one thing that we try is to partition graph into multiple segments, right? And then we can then feed each of the segment into the cost model to get the runtime for each segment and then do the summation to get the total runtime. And then you can then compare that to the target, right? And do the loss. However, this doesn't really solve the problem because if you do backward propagation on all the segments in the graph, you still need to keep all the activation around when we do backward propagation. And the majority of the memory consumed in the device is basically all these activations that you need to keep around, right? And if you have 100,000 nodes, you have to keep all of them around. So what we do is that, what if we only do backward propagation or gradient descent on just one segment, right? And then for the rest, you just do forward pass to get the runtime, but you can do stop gradient so you don't have to keep the intermediate activations. So simple idea, it turns out that it actually works pretty well. Also, it's not precise because we also ignore edges between the segments, but that doesn't seem to matter so much. So the result shows that this simple technique can actually enable training arbitrary large graph without much accuracy loss. The other problem, though, that we see is that these graphs can be very diverse, right? And there might be some similar graph that occur a lot in the training set. And for those, the model seems to do pretty well in terms of accuracy. But there are some graphs that don't appear that often. So for those, the accuracy could be pretty low. So we also like exploring different ways to make the model generalize better. And one of the idea is very similar to dropout that most people have known, where you kind of ignore some of the neurons, right? But instead of doing this at the node or like neurons level, we say, what if we drop out the entire segment? At first I'm like, okay, that's not gonna work so well, but it actually works quite well. So here is some preliminary result. And the first graph is to, on the training set, the top one is basically the one that with no dropouts, just the segmented model. But if you look at the validation graph, the blue one is the one that we apply the segmented model with the dropout, that drop the entire segment. And it shows better generalization according to the validation score. Oh yeah, the green one is the one with the dropout. So yeah, here in the training, it's not great, but in the validation set, it's doing better. So that's like, a nice surprise. All right. So, yep, question? It's actually random. So basically, at every training iteration, you randomly pick a segment to drop, or like a segment to do the backward propagation. Yeah.
Just go back to the earlier point. When you have the kernel level graph,
Mhm.
which has like, as you say, about like 10 nodes, couldn't you just like recompute everything in lookup table? Like, why do you need ML for that?
Yeah, so the question is that for the kernel level graphs, is it possible to just, pre-compute everything, put everything into lookup table? Like if we have seen this graph before, here's the answer, right? And I would say that not quite, because these 10 nodes are actually, because it's not just, like the node consists of the types of the operation, but also the size of the tensor, right? And these are multidimensional tensor, which means that you can't enumerate all possible graph that have 10 nodes, essentially. Yeah. But you can memorize the important ones, which we kind of do, which I'll go into later. Yeah. Yeah, another question?
It seems your graph is quite sparse. Do you
Yes.
think like graph of like a graph neural are even needed?
Yeah, so the question is that these graphs that we are looking at are quite sparse. Yeah, which is true, because I think each node is usually, a few inputs, one output, right? And the question is whether, like, when the graph is that sparse, do we really need graph neural network, right? Um, do you have in mind that we can use like transformer, LSTM, or just like concat everything together into a concat?
You have like 10 nodes, you can concat everything together.
Yeah. Well, we ran that experiment, and empirically, it's actually much worse than doing GNN. Yeah. So it seems like the connections is still important. Yeah. All right. All right. So the next part that we could try to apply machine learning to is to guide the search, right? So in this part, we also explore using different search strategy. So we consider a simple one, it's exhaustive search, simulated annealing, evolutionary search, and also more advanced search algorithms that use machine learning, including model-based optimization, deep reinforcement learning, or RL. I'm gonna go into a little bit of detail for the last two, so you understand what it is. So model-based optimization is actually a collection of different regression models to fit the data. These models, we consider rich regression, random forest, gradient boosting, and neural network. And we essentially, these regression model, the good ones, we assemble them to define an acquisition function, and then acquisition function is then used to optimize the evolutionary agent to generate the new batch of samples. One thing to notice here is that these models only learn from the configuration, and it does not encode the information about the graph into the model. So we have to train the model for each specific problem from scratch, right? So if you have the first model, you train, then you run the second one, it will start training from scratch. So it doesn't have knowledge about the graph. The other thing we try is deep reinforcement learning. For this one, it actually encodes the information about the program graph using very similar model to the learn cost model, where it have graph neural network to generate node embeddings. And then here we use recurrent attention layer, in particular transformer XL, to then generate the graph embedding. One thing that this model is different from a typical RL model is that it is not auto-regressive. So typically an RL model is auto-regressive in a sense that it usually do one small action at a time, So, and it would perform like a sequence of action, right, in an episode. But here, it will actually make a decision for all the nodes in the graph in parallel. And empirically, this is actually much better than using an autoregressive model, especially when the graph is very large. So we apply this model in our search algorithm. And I'm not going to the detail, but I add the reference here if you want to know more about the particular RL that we use. And here is the results on Fusion auto-tuning on 10 different benchmarks. The left side is the speed up over the default baseline, which is the production compiler, so higher is better. And the right-hand side is the speed up over time in terms of number of samples needed on one of the benchmark. And to our surprise, the simple search techniques like simulated annealing and evolutionary search is actually better and more consistent compared to RL and MBO. And our hypothesis is because the high dimensional search space make it really hard to fit an accurate model without prior knowledge. So it is possible that if we pre-train RL and MBO on a bunch of graphs and then test them on the test graph, it might do better, but we have not done that experiment extensively on this benchmark. So one thing we learned is that, advanced search techniques is not always better, and it really depends on the problems. Okay. All right. Any other questions before I move on to the next section? Okay. If not, let me try to briefly finish this one, the deployment. So I talked about how we built the autotuner, and we actually use this in production. So I'm going to tell you how we actually deploy this to tune all the machine learning workloads at Google. Well, one strategy is to ask all the user to run the autotuner on their workloads, right? So these are what we call offline autotuning. But in our experience, the user don't really want to change the way that they develop, their program. So it doesn't seem to work. The other thing is to integrate the autotuner as part of the compiler, but this will increase the compilation time significantly, right? So it doesn't work either. Well, so we end up with a strategy that I'll skip this one and tell you what we do. What we do is that we have a pipeline that collects what is the heaviest workloads that run at Google. So we have a Google-wide profiling that basically collects all the tensor computation graphs that the user run, and also it knows about like how many TPU hours and how many TPU devices it uses. So we can then have, here's the ranking of all the workloads in our data center. So every day we will run the autotuner on the top workloads and then save the configuration into the database, right? And this is back to one of the questions where they're like, can we just, memorize the graph in the lookup table and find the configuration? So in reality, when we deploy this, even when we use the learned cost model to accelerate the tuning time is still quite slow. So we don't want that to be the bottleneck for the user. So we end up doing this offline, save this into the database, and then we ship the database as an embedded database with the compiler. And then the next time when the user compile and run program, the compiler will check this database to see if there's a match. If there's a match, it will apply the configuration. Right? We also have a monitoring system that basically keep track of like which workloads is using the configuration, what is our overall like speed up from our techniques, and also to basically if there's something's going wrong. So we have deployed the tile size and flag tuning through this method to optimize the top workloads on our data center every day. And we also deploy the learn cost model, which helps us tune 20 times more kernels per day. And overall, we have seen about like 2% saving of the total TPU consumption time. And if we look at the saving versus tuning cost, we spend about 1 TPU to save about 15 TPU worth of time. And I think I'm gonna skip the rest, and then because we don't have so much time, and I'll leave the rest for questions.
There's a question.
Wait. I think it's gone. I'm gonna drink. Okay. So the question is, are you using the platform of AutoFDO for ordinary programs? Yeah. So AutoFDO is actually stand for automatic profile guided optimization. So originally, AutoFDO was developed for C++ program. And for the typical FDO, what it does is that it collects dynamic runtime information, for example, like how many times this loop is running and so on. And it feeds that information back into the compiler so compiler can make better decision. We use a totally different AutoFDO platform that we built specifically for XLA. And it's also quite different from traditional AutoFDO in a sense that our profile is the output from the autotuner. So it's used the output of the autotuner, feed that as a profile directly to the compiler and force the compiler to use that decision. Yep, the question? Yeah, let me go back. This one? Yeah. That's right. I would say that 2% it's very significant. It translates to a lot of dollars. And to go even more. Yes, I think so. I think we can do better. So far we only deployed the tile size auto tuning here. We have not deployed graph level auto tuning like layout and fusion. And we actually have an estimate that for the graph level auto tuning, you can get up to like 10% speed up. So we are hoping that we can deploy that in production. There is another question.
A couple of questions as well.
Oh, okay.
So this one's first.
Okay, this one say, I imagine that we need a model specific to each hardware. It is possible and valuable to train generic model that can estimate performance across different hardware. Yes, for my opinion, I think it would be really great to have that. And not specific to TPU, but like think about like various different types of CPU, right? Like Intel have different version of their hardware or like microarchitecture. ARMs also have their different variants of their microarchitecture. And they are not that much different from each other, right? So having a model that train, for all of these variants could be really useful. And in some really like practical contexts, for example, if you want to run machine learnings on phone, right? If you look at phone, there are so many types of CPUs that run or like accelerator, right? And if there's like a new generation of phone coming out, if we have like a share model, it will be really easy to fine tune for that new hardware, right? So I think it's very valuable to have that. All right, next one is, can you use hierarchy reinforcement learning to help on policy to guide policy with some scope? I'm not too familiar with hierarchical reinforcement learning. It's possible, but I think I need more information to see whether it will help or not. Yeah. Okay, I think that's all from the online. Okay.
So any heuristic on what type of like operation that you get like massive like gain or not? And is it like because of the baseline is bad or because like that any magic trick that can optimize?
Yeah, I wouldn't say that the baseline is bad. um, well, from the fact that actually Google cares so much about the TPU, and they have like a pretty big team of engineer that continuously improving the compiler. But one thing that it's not good is that usually when the engineer develop these heuristics, right, they have some of the benchmarks in mind, and they will be like, oh, how can I improve the heuristic to make these benchmark run faster, or like these important models? And then there might be like a new models coming up that is like different from the one that they are looking at, and suddenly the heuristic might do pretty bad on that. Yeah, so I think we see this scenario quite often.
Another question. I actually have one question in the earlier slides where the heuristic is better than your model. Do you have any comment on that?
Is it at the cost model?
Yeah, the cost model. Yeah, just the evolution.
Yeah. Oh, I don't think we haven't investigated too much, but um, you know, human model overfit to like human knowledge. um, um, so it could be like one of the very important model that they were like, oh, how to optimize for this one. And yeah, and like learn model, it's like overfit to the data. So if the data doesn't fit that, program very well, it will tend to do worse. Yeah.
And I think in the previous slide, right, there's a breakdown on speed up from different type of like subroutine or something, right? That's like different by different model. It look like really different from different model. Are there any comment on that? Why like different type of model like just gain from only one specific
Yeah, the question is that there's a slide that we have like the breakdown of the speed up from different kinds of optimization. And there's not like a trend that, oh, like this optimization, it's way better than other. It's just like very different model have different breakdown, right? Um, Good question. I think I actually don't have answer to that question, I would say. Um,
I can say on something because the first one is speech. Speech models are unnecessarily large usually. We just take take some model from like vision people, and we usually know that it's unnecessarily
you
large.
want to speak with the mic?
So I'm not surprised that most of the gain are from fusion. The rest I'm not so sure. But yeah, usually we know that speech model are like broken. But yeah.
Yeah, I guess there's some like micro trends. So if you see that these are all different kinds of GraphNet, and then they have like similar breakdown. Yeah.
do your model like aware of the like type of model that they're working on? Like are there any context?
There is no context other than we feed the graph to the GNN model. Like if we have like if we apply the GNN model, that's where the context might come from. But if we don't use the learn cost model, then we don't feed any additional information to the autotuner.
There are several variants of what happens if we implement TPU and or something like that. Would the learn cost be generalized?
Yeah, so in our experience so far, they actually seems to general. You still have to do some fine tuning, right? So there was like this slide that I talked about for the kernel level model where you can essentially freeze the GNN parts, and then you just need to fine tune the last layer. I think this one. Yeah, and we actually do this in production. And it seems to work pretty well across, I think it was like 3 generations of TPUs. Yeah.
Do TPU team work with you on try to optimize certain operation on TPU be better at workload?
Yeah, well, so we collaborate closely with the compiler team. I don't interact with the TPU like hardware team directly myself, but there was also questions about, oh, like some of the knowledge from the autotuner might help designing the new generation of TPU. Like there was some of that, but I have not engaged with them directly. Yeah.
Actually, experience than follow-up code, the more impossible. Hardware have, I mean, underlying hardware have very strong constraint on what type of hardware can be possible. If you can think of some, say, instruction, you find out very. Also, the other thing is that super instruction is so much better. So we did attack has been done before in trying to do a kind of AI which is extremely fast. And the team find out that building software optimizer with compiler is 10 times have longevity than building special hardware. So, but that's 20 years ago. So
Another quick comment on this. I'm curious, like, since your compiler change every day, basically, right? Do you get any complaints that the code runs differently, the same code, but like how everything changed, like the usage change or something like that? I can't predict anything.
Yes, yes. We get complaints from user from time to time, where they're like, so like at Google it's like this like mono repo, right? And everyone can see like all the change that happen. So for us, we have this automatic tools that like checked in these configuration every day, right? And when things goes wrong, what user usually do is that they can do like bisecting. And sometimes they will bisect and they were like, oh, our auto-generated change caused something's wrong. Most of the time it's things like accuracy loss. And so one thing, right? So most of the time, the optimization done in the compiler is semantic preserving. So semantic shouldn't change, but that's usually only with real number, not floating point. What for for machine learning, we deal with in reality we deal with floating point, and the optimization that happen in a compiler, like picking different tile size that actually affect the order of the reduction that happen in your program, which actually affect the numerical result. And these numerical result, for most of the time, it doesn't really change the accuracy of the model a lot, but for some model, it actually changed the accuracy. So we do get complaint from user like, oh, why is your automated code change our accuracy? And like our accuracy is now like 5% lower. So we do get that complaint from time to time. But we are working on some mechanism to try to guarantee some sort of correctness. Obviously, it's not, 100%, but, it should be able to kind of filter out some of the obviously bad configuration. Yeah.
Any other questions? Last one.
So just wondering, like, I think there is a graph that show a lot of like, and then also one is show
I think it was this one.
So you say like you always show the one that have like more than 5. Just wondering, is there any kind of workload that have like regression, like increase?
Yeah, no, because we usually start from the default configuration, and if we search for a long time, we don't find anything, it would just be the default. Yeah.
And
Yes.
another, like, the next question is, if, let's say, just wondering, are these kind of, like, latency critical workloads, or they are, like, unattached?
There are mix of both. So yeah, like so like the actual workloads that we tune every day, there are some actual like serving workloads that run in production. But there's also a lot of like large, like long running training workload as well. So those are more like batch.
So just wondering for the latency critical workloads, how can you, when you say like, oh, it changes every day, how can, let's say, the user can reserve enough resource to guarantee their SLO.
Yeah, so the question is that like since we checked in these profile every day, changing the compiler every day, how can we make sure that those like latency sensitive workloads is actually like under like it's actually like we're not regressing those ones, right? So we have a lot of integration tests. So like the teams that responsible for these serving models, they have their own testing pipelines. And what usually happen is that when they update, get the latest version of the compiler with the newest profile that we checked in, they will rerun all the testing that they have and make sure that everything is under the time budget that they have. Yeah, so it's basically a different testing pipeline to guarantee. Like if nothing goes wrong, the configuration that we put in the database should only make your model run faster and not slower. But there's always bugs, so you never know.
I understand it's always faster than baseline, right? Because if it's slow,
Ye-
you just use the baseline. But if it's like today is 5% faster, next day is 3% faster, you have some regression.
Oh yeah, so there might be I didn't talk about that part. So we also have this thing that call like profile cop that basically it like run all the checked in configuration every day to make sure that if there is a profile that now stale, not valid with the current version of the compiler anymore, we're gonna remove that from the database. Yeah.
Does it make sense to add like snapshot system where people can pin them to like specific version of your compiler, so that like I mean if they want to update it they can, but like if they want consistency they can also just like leave it at version.
Yeah, it's like Google, it's like its own world, People at Google, people, yeah, the versioning system is very different from like the rest of the world where, like normally you don't, a compiler probably update, I don't know, once in a month or something, right? Like it doesn't update that often, but at Google, because of the monorepo environment, it update every second. Not the compiler, but the compiler might update every hour or something like that. And like we tend to encourage people to run code at the latest version. And if your code sync to something like a year ago, it doesn't guarantee that it will work anymore. Yeah.
So thank you for the enjoyable talk. I think there's a lot of fun discussion, more than I thought, considering the topic, which is very specialized. But I think it's everybody probably get something from this talk. Also, let's thank the speaker again. Yay! And yeah, so enjoy the rest of your days. Uh, See everybody, and hopefully we get more these kind of talks later on. So if you have anything to share